going to continue with our chapter on the mole today. Your quiz grades show that you are very comfortable converting quantities involving the mole. Very successful in calculating percent compositions from chemical formulas. As I mentioned the other day, you have to be able to do it from laboratory data as well. So you really want to look over your labs to make sure you know how to calculate the percent of water experimentally. That is from laboratory data. Make sure you all understand how you calculated that. That's a very important concept that will be assessed on your test next week. Today and next time we're going to learn how to determine empirical and molecular formulas. And you'll see that all of this is interconnected. Your quiz showed that you know, for example, if you're given a chemical formula such as calcium chlorate, you know how to determine the percent of calcium, the percent of chlorine, and the percent of oxygen. And most everybody was highly successful there. I would say some of you do want to review formula writing. There's still a little bit of murkiness in there. Not so much in this class, but that's a concept that must be mastered for success in chemistry. If you're still struggling with formula writing, go back and review Chapter 5, Classwork 2.1 and 2.2. What we're going to do today is another type of elemental analysis that we mentioned the other day that is used in CSI determination. We're going to do it backward. From percents, we can figure out chemical formulas. First empirical formulas and then molecular formulas. And we've introduced a couple of terms here that you are probably unfamiliar with, so we're going to define empirical and molecular formulas, and then we'll walk through the steps to do this determination from percent to chemical formula. Really very simple. Follow through on the steps. You'll have a ton of practice today. You'll walk out today feeling very confident with it. So in your notes then, we're going to pick up at the empirical formula position. Again, this is a type of elemental analysis. And an empirical formula is a chemical formula, and it represents the simplest whole number ratio among elements of a compound. So when you look at the simplest whole number ratio, it has been reduced down. They do not have a greatest common factor other than 1. For example, CH2O and NO2 are empirical formulas. Anytime you have one of an element, it has to be an empirical formula because a 1 can't be reduced down. NO2, you have 1 of this to 2 of this, and that's a ratio. A molecular formula would be something like this, C2H4O2, where you don't have the simplest whole number ratio because each of these is divisible by 2. Now, if you divided each of these by 2, you'd get CH2O. So this is a molecular formula. Its empirical formula happens to be CH2O. C2H6 is a molecular formula. Both of those numbers are divisible by what? 2. And so the empirical formula of C2H6 would be CH3. Do you want me to write it out? Are you seeing it? You got it? Write it out or you see it? You see it. Okay. And then next you have C4H12N8. That one I'll write out. So you have C4H12N8. And this is an empirical or molecular formula. This is a molecular. A molecular formula is a multiple of an empirical formula, and we'll talk more about molecular formulas next time. So this is a molecular formula. To get the empirical formula, then, we would divide by what? Good. And this is a little sloppy. This is EMPI. This should be an R in case it's not clear as such. So you would divide by 4 and you'd get CH3N2. So we're going to learn how to get an empirical formula from percent comp. So if we're given the percent of carbon, the percent of hydrogen, and the percent of nitrogen, we can work backward and get the empirical formula, and then next time we'll then go from empirical to molecular, which is actually much easier than getting the empirical. Let's make sure you've got the empirical molecular formula concept down. CH4, empirical or molecular? Simplest ratio, empirical. One thing I do want to mention, though, you're not incorrect in yelling molecular. Some molecular formulas are empirical, and some empirical are molecular, depending on what it is. We'll take a closer look at that, and I'll show you what I mean there in a little bit. But C2H4, you know, is molecular. It can be reduced down. CH3F is empirical anytime you have one of something. C3H6N is empirical. C3H6N12, molecular, divisible by 3. Look at this one, C3H6S2, empirical. They don't, 2 and 3 do not have a greatest common factor. Be careful there. That's not reducible. Does that make sense? So if you had something with like C5H7, that's also going to be empirical. You can't reduce that down. All right, and that's where the math really comes in, just the baby math that you learned back in probably 3rd, 4th, or 5th grade. All right, to determine the empirical formula, we're going to follow some steps. Some of the steps won't make sense right away until we actually do it, and we're going to walk through numerous problems together to the point where you will be good to go, and you'll be able to do this on your own by the end of the period. So to determine the empirical formula from the percent comp, the first thing you need to do is literally just change percent to grams. There's no calculation involved. If they give you the percents and they all add up to 100, you just change percent to grams. No calculation. Then you're going to convert grams of each element to moles using the periodic table and molar mass. That's why it was important that we assessed whether you could do a simple mass to mole conversion. And you felt very comfortable with that. I don't foresee any difficulty in step 2. Here comes the new stuff. You're going to determine the whole number ratio of elements in the compound by dividing moles of each element by the smallest number that you have. I'll show you how to do that. You're just getting a ratio, so by dividing them all by the smallest number, you'll set one of them at 1, and everything else will be 1 or greater than 1. If the numbers that you get after the division are whole numbers or within 0.05 of a whole number, you'll write the empirical formula using the number of moles as each element subscript, and I'll show you exactly how to do that. If when you divide you don't get whole numbers, there's an additional step to do, and we'll focus on that in about 15 minutes once you have the framework of these 4 steps down cold. These steps may seem a little bit frightening at first, but we're going to write each step as we go. We'll label it, and I think you'll find this to be very straightforward. I find the kids are very, very good at it. Just watch your sig figs and watch your units. We're going to walk through a series of examples together. The first example says, a new alkaline battery is found to contain a compound of manganese and oxygen. Its percent comp is 63% manganese and 37% oxygen. And you want the empirical formula. We're going to walk through this step by step, and I know you'll be very successful with this type of analysis. I have 63% manganese. I'm writing the percent in pencil. You'll see why in just a minute. And I have 37% oxygen. I'm trying to figure out the empirical formula. That is Mn, some subscript, which I'll call X, oxygen, some subscript, which I'll call Y. When you do empirical formulas, those subscripts are typically X, Y, and Z, or if you have 4 elements, W, X, Y, and Z. It doesn't really matter what you call them. You'll see later on coefficients are typically A, B, C, and when we get to kinetics, the superscripts are going to be N, M, L, and it's just where you start in the alphabet. But I've seen this done with ABCs. Whatever rocks your world is fun. The first step is simply to change percent to grams. No calculation involved. Easiest step imaginable. I'm going to erase those percents and just put grams in. And if I were doing this problem for myself, I wouldn't have even written the percents. I would have automatically gone to grams. Keep it simple. But I wanted you to see where it came from. The second step is to convert mass to moles. And you already know how to do that. You know that 1 mole of anything is equal to the mass in grams off the periodic table. And you have 54.938 grams of manganese per mole, molar mass. You're going to do the same thing for oxygen. 1 mole of oxygen, 15.999 grams of oxygen. So you have 63 divided by 54.938. Watch your sig figs here. You're given 3, stay with 3. And that's 1.15 moles of manganese. And that's 2.31 moles of oxygen. And again, this is step 2, the conversion of mass to moles. And that you were very successful on your quiz, so I don't foresee any problem. The next step is to get the simplest whole number ratio. You are going to divide each of these by whatever number is smaller. 1.15 is less than 2.31. You only divide by the number 1.15, and you do the same to this. When you divide that, you get and I've run out of room here, so I'm going to continue here. 1 mole of manganese and 2.01 moles of oxygen. The division step is very often the one that kids forget, so be very careful there. That's step 3, to divide only by the number. Maintain these units. A lot of you are very sloppy with your units. You've got to be very consistent here. It makes a difference as you go. The last step is to write the empirical formula. This number is within 0.05. Actually, it's essentially a whole number. So this is 1. This is within 0.05 of a whole number. So this is 2. And now we're going to use that information to write our empirical formula. The other thing I want to mention in regard to this is some of you did this really cockeyed on the project. Remember with ionic compounds, it's always cation, then anion. And a lot of you mix that cation in somewhere because you picked very complicated chemical names. So keep it simple. And so cation first, that would be a 1. Oxygen with a 2. You don't write 1s in chemical formulas, so it's just this. Here is your empirical formula. And that would be step 4. And again, the steps, when you read them, you're like, oh gosh, what's she talking about? Here we go again. But when you label it down like this, you can see each step in action, and I know you can be very successful. Now, you don't have to label those steps. That's just for you in case you're doing some problems and you get stuck. You'll know what we did. Carefully. Raise your hand and name that compound. Carefully. Got a transition metal. Does it need a Roman numeral? Yes. Name the compound. Volunteer, volunteer. What's the charge on oxide? 2 minus. 2 times 2 makes manganese. So it's manganese 4 oxide. Correct? Alrighty. Let's do the next one. The next one's a little harder, but you'll be fine. Super bright class. You should do very well here. It says, determine the empirical formula of a compound that's 74.03% carbon, 8.70% hydrogen, and 17.27% nitrogen. So again, we're going to get those, and rather than writing percents, we know we need grams, so why write and erase? Just more busy work. We hate busy work. 74.03 grams of carbon, 8.70 grams of hydrogen, 17.27 grams of nitrogen. First step complete. What do we do next? Convert mass to moles. So 1 mole of carbon to 12.011 grams of carbon. 1 mole of hydrogen to 1.0079 grams of hydrogen. 1 mole of N, 14.007 grams of N. And we're going to get moles of everything. Is this step clear? This is back from last week. And that's why I've said chemistry is such a building process. If you don't master early concepts, They really come back to haunt you. It's a lot like math. So now we have moles of everything. And what do we do? Go ahead, Haley.
Divide by 1.233.
How come you picked that number?
This is the smallest.
You got it. Excellent. So you're going to divide all of them by the smallest number. And again, that is the most common mistake that kids make. They forget that step. So watch your Siggies. We've got 4.999 moles of carbon. We've got 6.99, actually I take that back. Because that's in 3 sig figs, I had 6.999 in my calculator, but 3 sig figs right away make it a little simpler. And that's going to be 7.00 moles of hydrogen. And this is, of course, 1.00 moles of nitrogen. And all of these numbers are within 0.05 of a whole number, making it super easy. This is 5, this is 7, this is 1. And when I write my empirical formula, I'm just going to keep it in the same order. It makes life easier. C5, H7, and that's my empirical formula. Ionic or covalent compound? Is there a metal in there? Definitely covalent. How do you feel about it? It's not too bad, right? Try the next one on your own. It's on the screen. See if you can do it. The answer is there. Remember percent to grams, grams to moles. And just make sure you're writing things out in their entirety. Don't forget your units. Don't forget what the element is so that really can go through. Once you look like you have your moles, then remember the next step. And some of you, I think, have got this already, so you're starting to move ahead. I'd stop at that dead alkaline battery. That one's going to be a little bit different. If you want to get your moles out, fine, but you're going to see something funky in there. How'd we do? Got it? All right. You can draw these compounds too. Cyclohexanol is a real cutie woody one. Looks like this. It's cute. Cyclical, 6 carbons in there. In any event, what we've done so far is we have determined empirical formulas, and when we divided by the smallest number, we always got either whole numbers or within 0.05 of a whole number. So it was really pretty straightforward. Sometimes when you divide by the smallest number, you don't get whole numbers out. One of them will always be 1, but the others might not be whole numbers. You may get like 2.5 or 3 1/3, something along those lines. And then there's one additional step, and that's what you're going to see here in the dead alkaline battery. In step 5, it says if the numbers are not whole numbers, multiply each of them by the smallest whole number that will make all of them whole numbers. But you have to multiply each one by the same number. And then write your empirical formula. And this is a little trick that I've taught kids over the years, and they said it's been very helpful. Let's say when you divide, you get something like 1.20 moles of something, or it could be 6.20. I'm focusing on the numbers after the decimal. So 0.20 is 21 hundredths, or 2/10, or 1/5. The multiple will always be the denominator of what that decimal is as a fraction. So you would multiply everything by 5. If you got 1.25 or 4.25 or anything 0.25, 0.25 is 25 hundredths, or 1/4. So the fraction right here is equivalent to this piece, and you would multiply by the denominator of the fraction, which is 4. If you got 1.33 or 3.33, you'd multiply everything by 3, because 0.33 is a third, and the denominator of that fraction is 3. If you got 1.50 or 2.50 or 5.50 or anything 0.50, 0.5 is equivalent to a half. So you'd multiply everything by 2. If you got 1.67 or 3.67 or anything 0.67, 0.67 is 2/3. You multiply by the denominator of the fraction. So you'd multiply by 3. If you get 1.75 or anything 0.75, 0.75 is 3/4. So you multiply by the denominator of the fraction. And if you can remember this trick, you'll be very successful with the more complex problems, which is more apt to be what you're going to see based on the fact that you're so bright and you want to be challenged most of the time. A dead alkaline battery is found to contain manganese and oxygen again, but the dead battery's percent comp has more manganese now than it did initially and less oxygen. We want its empirical formula. We're going to process this the same way, but when you divide by the smallest number, you're going to see you don't get whole numbers out. So we have 69.6 grams of manganese and 30.4 grams of oxygen. And you process this the same way we did with the first problem. 1 mole of manganese, 54.938 grams of manganese, 1 mole of oxygen, 15.999 grams of oxygen, and that's 1.27 moles of manganese, and that's 1.90 moles of oxygen. Once I get moles, what's my next step? Divide by the smallest number. And that's going to give you 1 mole of manganese and 1.50 moles of oxygen. So this is the first time we didn't get whole numbers out, but we're not going to panic because we know what to do. We have to multiply both of them by the smallest whole number that will make both of them whole numbers. I focus on 0.5 and I recognize that as what fraction? A half. So I'm going to multiply both of these by 2. And that's going to give me 2 moles of manganese and 3 moles of oxygen. And a dead alkaline battery then, we have Mn2O3, or manganese 3 oxide. Make sure you multiply both of them by the same number. And if you have multiplied them, you will not have something with 1 in it anymore. How are we doing? Let's do another one a little bit harder. The next problem says determine the empirical formula of a compound that's 32.02% carbon, 6.046% hydrogen, and 61.93% phosphorus. And you could draw the compound if you wanted to. Always good practice, and you like drawing compounds, and you're exceptional at it, so it's fun. We've got 32.02 grams of carbon. We've got 6.046 grams of hydrogen. I'm changing percents to grams right away. And 61.93 grams of phosphorus. What would my next step be? Convert to moles. So you guys are all going ahead because you've got this. The only thing I would say is really be careful of your setup here. A lot of kids have numbers all over the place with no units, and it's impossible to follow. So be meticulous in your setup. It will serve you well. So all of that from the periodic table, you're all very strong with that concept already. And we have 2.666 moles of carbon. .999 moles of hydrogen, maintaining my sig figs. And 1.999 moles of phosphorus. Once I get moles of everything, I need to do what? Divide by the littlest number, just the number. And again, that's the most common error. It's one of the reasons I'm doing it in a different color. Really want you to pay attention to that. 1.334 moles of carbon. .001 moles of hydrogen, and 1 mole of phosphorus. And you'll note I've still labeled everything moles with the element. Much easier to follow, really need it. Do I have all whole numbers? No, this essentially is good. This is good. This is not within 0.05 of a whole number. Focusing on this piece, 0.334 is equivalent to what fraction? 1/3. So I'm going to multiply everything by 3. And that's a common boo-boo too. Kids will only multiply a piece. Multiply everything. All right? So we're going to have essentially 4 moles of carbon, 9 moles of hydrogen, and 3 moles of phosphorus. I knew I was getting whole numbers, so at this point I'm not going to maintain all those siggy-wiggies. And I've got C4, H9, P3. Now, a question came up in 5th hour, and it may be in the next problem too. So let's take a look at just a simple scenario. You're good on this one? Let's say if after we divided, we came out with this. I'm going to put a different element here because it's a different problem. I don't want you to be confused. If I came out with this, a quarter is similar to what fraction? And this is 1. So what would my multiple be here? 4. And that's one thing I wanted to mention. You'd multiply everything by 4, and you'd get the simplest whole number ratio. So if the fractions are not the same, just go with it. If you had a situation where you had a half and a third, you would multiply everything by 6. You've got it. All right. I would like for you to try the next problem. Before we do that, I just want to make a couple things clear, because we've been going for a while and I want you to have a lot of practice time. I'd like you to try this problem, which is very challenging. The answer is there. I'll take a look what you've done. You can do this problem as well. And then in your classwork, the problems that go with this section are 24 through 27. If you feel like you need more, I'll give you more. I also have a review sheet for you for this test. It's all problem solving. But at this point, you should feel somewhat comfortable writing empirical formulas. You'll see how empirical formulas fit into this whole mole concept that we've been talking about. And again, when you walk out the door today, you should feel pretty comfortable with this concept. We'll learn molecular next time, which is easier, and we'll put it all together and get you ready for your test next week. Any questions? All right, so these are the classwork problems that go with it. You did extremely well. If you have any questions, please ask. And when you're ready to work in groups, then that's what we'll do.